Hello, I'm going to review a few slides from Chapter 8 after class so that we can just do a few extra problems and examples on Lewis structures. So let's look at this question here. It's asking which molecule has only single bonds and not double bonds in its Lewis structure. Let's look at ClO minus first. So I have 7 plus 6 plus 1, 14 electrons. Diatomic molecules, I want to satisfy the octet rule when possible for both atoms, and it is possible using a single bond, kind of like Cl2, 14 electrons, and I have a minus charge on oxygen, a 0 on chlorine, so a good Lewis structure here for ClO minus. So single bonds and double bonds, got that true for ClO minus. ClF3, 7 plus 3 times 7, 28 electrons, so ClF3 goes chlorine, fluorine, 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 lone pairs on the non-centrals. That's 8 electrons per F, that's 24 electrons. 4 electrons left over onto chlorine. And so only single bonds here as well. This is actually 0 formal charge all the way around, just making sure that we're not making double bonds or anything here. So ClF3 only has single bonds. Now SO3, we have essential sulfur, we have 4, well, I guess 4 times 6 valence electrons. 6 for sulfur, 3 times 6 for O. 4 times 6 is 24 electrons. So essential sulfur, 3 single bonded O's. We might start with the lone pairs. O. And then we might recognize a 3 plus charge room for an octet. We at least make one double bond here, lose these electrons here, and then we have a 2 plus charge. Now we can keep going. If we want to satisfy the formal charge rule, this goes to plus, then we move in here and go to 0. And so we can either have 3 doubles or at least one double. So we at least have one double bond in SO3, if not 3, depending on if we're satisfying the formal charge rule or if we're stopping at the octet rule Lewis structure. So we at least have one double bond. Either case, the 3 SO bonds are the same length, 4/3 order here, and all of them double or 2 in the formal charge rule structure. So we'd be at only 1 and 2, or both 1 and 2, having only single bonds. So NCO, so N to C to O is our connection here. Our count would be 5 plus 4 plus 6 plus 1, minus 1 charge. And so that is 16 electrons. We start here, this structure here, 2 plus charge here. So the question kind of becomes, do I do this? That looks good. And then do I do this? So, or do I do maybe a triple bond between the N and the C? So let's go through these permutations. And so if I just stop here real quick, I go to plus with 3 bonds. And if I go to 4, so, and let's just think about what the possibilities would be. So if I go to 4, all right, the 1 in here is this structure there. And so this structure here is going to have a 0 formal charge, a 0 on carbon, and a minus 1 on nitrogen. Or I could do, let me go back to the structure here for a minute. 2 plus again, and I can do this here to go to double. I've lost those electrons here. And then I could go to, what about triple here? Get rid of those electrons here. And so I go to triple, and that takes this charge, of course, to 0, and then minus 1, and then 0. And now I could even go another time and say, well, what about C triple bond O here to nitrogen single? This is so bad you might not even consider this. 2 minus plus, oxygen going plus, nitrogen going 2 minus, makes no sense. So that's definitely wrong. And these two structures here, how can we make sense of these two structures? Well, look at it first. All the atoms are satisfying the octet rule. So we can't, sometimes we might rule out a structure if one atom's not satisfying the octet rule and the other one, all of them are. So all of them are satisfying the octet rule in the same way. But if we're going to choose between putting the negative charge here or here, oxygen is more or less negative. So we want to put the negative charge in the more or less negative oxygen if all else is equal. So all else is equal. So we go with this Lewis structure being best. With the triple bond between N and C, single bond between C and O, because we get the more negative charge on the more electronegative atom, as opposed to on a lesser electronegative atom. Okay, now N2O, a little tricky here, but N to N to O is the order. That's two N's, then the O. And so getting the connection right first, NO2, N2O is 16 electrons as well. This is nitrous oxide for those who are curious. So this is 16 total electrons. So we start with this Lewis structure here like we started with before. Same issue as we had before. And so then we can end up with the N double bond O plus minus 0, or N triple bond N single bond O plus minus 0, or the really bad structure, the analogous N triple bond O with the plus on the O, still plus on the N, and this is N O, so this will be N with a 2 minus. So I got 1, 2, 3, 4, 5, 6, 7, 5 minus 7 minus 2. So this one's definitely the worst. And then this one's definitely the best. Now there's one other structure sometimes you'll see that is wrong. Now why would this be wrong? You might think, well, minus plus, what about this? And triple double to O. See, this is just if I take this electron pair here, move them in to make that double bond, I reduce the formal charges now to be 0 and 0. This looks really good, right? But the problem is an expanded octet. So we can't do this. So that's not the best Lewis structure for N2O. So this one here is the best. Multiple central atoms. So, CH3, and then COOH. I just have the O and the O on the same carbon. And then hydrogen here. How do I get my electrons? Well, you can kind of go non-central, positive charge. Let's make a double bond. So that's how we do this one here. And then lone pairs on the oxygen here, we'd have 2 extra electron pairs left to go if we counted them all up. One thing that we'll see as we get to chapter 9, carbon tends to form 4 bonds. So for stable organic molecules, you can almost always use this rule that carbon's going to form 4 bonds. Now it could be 2 double bonds, or 1 double bond. So 1, 2, 3, 4 bonds here. Oxygen tends to form stable compounds with 1, 2 bonds, and then 2 sets of lone pairs. And so 1, 2 sets of bonds for the double bond between the other O, and 2 lone pairs. Nitrogen tends to go 3 bonds, 1 lone pair. So if you use these ideas, you just kind of, that CH3 is on the one end, that's easy enough. And then C to N is our connection. And then if nitrogen forms 3 bonds in a lone pair, carbon forms 4 bonds, we're good. So this is CH3CN. C2H4, again, if you're picturing two hydrogens on each carbon, the carbons bonded together. If I'm going to get 4 bonds to carbon, only way I'm doing that is with a double bond. So it satisfies each carbon having 4 bonds. Xenon F4, 8 plus 4 times 7, 36 electrons. So central xenon, 4 fluorines, single bonded, lone pairs in the Fs. That's 8 times 4, that's 32 electrons. 4 electrons left over, onto xenon. Doesn't matter where you write them. So that's xenon with 2, 4, 6, 8, 10, 12 electrons. So xenon has an expanded octet, and that's okay. This is only forming because the fluorines are trying to pull electrons off the xenon. BrO3 minus, so 7 for bromine, like chlorine and fluorine, plus 3 times 6 plus 1. That's 26 electrons. So we're going to get central bromine, 3 oxygens, lone pairs on the O's. kind of need to do this because if we don't do this, we may not know if electrons go on bromine. So that's 24 electrons. So we have 3 times 8. That's minus 24 electrons. That gives us 2 electrons left over. Let's go on bromine. Now we're good here with the octet rule. So this is the octet rule structure. And then you can also minimize the formal charges. 1, 2, 3, 4, 5. We got a +2. So we can minimize our formal charges with double bonds. That then would resonate through the molecule. And so pi system electrons would be these two, those two, and then the other double bond electrons. So 6 electrons in the pi system. So 6 pi system electrons here for BrO3 minus. And then we have a localized bond. We don't have a pi system. We just have one pi bond here for C2H4. Periodic table, I gave this just to, if we needed to refer to a periodic table in the notes. And I think that was the last question. Oh, let's look at one more question here. So bond length trends for NO minus, NO2 minus, NO3 minus. I kind of alluded this in the notes today to a problem like this. And so the way we, according to their Lewis structures that obey the octet rule, which I don't even really have to say because these are second row atoms, they have to satisfy the octet rule. Rank the NO bond lengths in order of increasing distance based on their bond orders. 5 plus 6 plus 1, 12 electrons for NO minus is N double bond O. Minus is on the end, but that's okay because that's the only way I can sketch a Lewis structure where we satisfy the octet rule in both atoms. So double bond here, bond order is 2. NO2 minus, 5 plus 12 plus 1, that's 18 electrons. So nitrogen, oxygen, oxygen, that's 16 electrons. So we have 2 left over to go on nitrogen. And then I have a plus charge on nitrogen. So I can pull in 1 double bond, and then that can resonate to the other side of the molecule. And so then I have 4 electrons in the pi system. And then I have a 3 halves bond. So I have 1, 2, 3 bonding pairs of electrons spread across the 1, 2 connections of the atoms. So bonding pairs, so count the lines, and then bonds, count the connections between the atoms, the 2 NOs. So 3 halves bond for NO2 minus, and then NO3 minus, 5 plus 18 plus 1 is 24 electrons. So central nitrogen, oxygen, 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 lone pairs. So that's all of our electrons. So all of them are used up, no lone pair on nitrogen. And then I can make one and only one double bond in our Lewis structure here that then can resonate with these 2 and 4 electrons and also with these 6 electrons. So 6 pi system electrons for NO3 minus. And then I have, let me use a different color pen, I have 2, 4, 6, 8 electrons. That's 4 pairs of electrons being spread across the 1, 2, 3 bonds between the atoms. And so 2 is, this is a numerical value. 2 is greater than 3 halves. It's greater than 4 thirds, just numerically. And so this is my double. And then this is my NO3 minus. This is my NO. 2 minus. And so this is going to be the shortest. And this is going to be the longest. Because we're getting closer to single. Bonds are shorter the more electron pairs they have shared between the nuclei. And so in terms of increasing length, we're going to have NO minus is the shortest, NO2 minus next, and then NO3 minus being the longest. So rank these in increasing order. So it should be 1, less than 2, less than 3. So, yep, chapter 9 deals with shapes, polarity, molecular polarity, and some bonding models. All right. Thanks for the attention in this extra video.